Hello students, in this video we'll use the residue theorem to evaluate an integral that is related to the gamma function. This integral needs to be evaluated using a keyhole contour, which is a very interesting technique in contour integration. Let's first of all, let C be a number between 0 and 1, and consider the function, the integral from 0 to infinity of x to the negative c over 1 plus x dx. This is clearly a convergent integral, right? Because c is between 0 and 1. And so let's evaluate this. We can evaluate this with the residue theorem. Okay, and how do we do this? We're going to construct the function. So let's f of z be z to the negative c over 1 plus z. Now, of course, what is z to the negative c? So z to the negative c is going to be what? So z to the negative c is going to be the exponential of negative c log z, and there is, of course, our logarithm. And of course, remember our rules. Whenever I have a logarithm of the problem, I need to specify a branch cut. So we need a branch cut to write this down. So we need a branch cut. You can pick your favorite branch cut. And one of my favorite branches is prime branch. Okay, excellent. So we need a branch cut. So what's this branch cut going to be? So log of z is the real log of the modulus of z, okay, for z not 0. And then plus I argument of z. And now argument of z is going to be between 0 and 2 pi, but not any of those values. So here, that's my branch cut, arg z less than 2 pi. Okay, and what I'm going to do now is I'm going to draw a contour. Here's my contour. That's a circle of radius r. And there's going to be a narrow alleyway over here to a circle of radius little r. Okay, so that's my keyhole contour. So it's called a keyhole contour. Okay, excellent. And of course, this is going to be the origin. So that's the origin 0. And this is, of course, is going to be a small circle. So that's going to be, I'm going to call that c little r. That's a circle centered at the origin of radius little r. And this big circle over here is going to be cr capital, okay? And so what's going to happen over here is as I let this r go to 0, what's going to happen is that as r goes to 0, this radius goes to 0, this narrow corridor is going to collapse, right? So these angles over here, the theta over here is going to decrease to 0, and theta over here, the argument over here is going to increase to 2 pi. And that's going to be the essential idea behind the proof. So when I do the portions of my contour that go over this horizontal piece over here, around the circle like this, the big circle is oriented counterclockwise, and the little circle is going to be oriented what? The little circle is going to be oriented clockwise, right? Like so. And that's going to be opposite oriented, okay? Excellent. And of course, this value over here is going to be the value big R, and that value there is going to be proportional to little r, okay? Excellent. So that's our contour. Let's call this contour over here gamma. That's the whole contour. So it's gamma of little r, big R. And so by the residue theorem, the integral over gamma little r big R is going to be what? Of our function over here of f of z dz is going to be 2 pi I, the residue of f. And where's the singularity of this function? The only singularity of this function is at -1, right? So there's my only singularity, -1, which is going to be 2 pi I, and then what? And then, of course, it's a simple pole, so I just plug in what? I'm just going to plug in the -1. Of course, the argument there is going to be pi, right? So the argument of that singularity is going to be pi. So it's going to be, of course, the modulus of -1 is 1. So it's going to be e to the what? E to the, where's my function over here? It's going to be e to the negative c, and then I pi. So it's going to be negative c I pi, like that. Excellent. That's my residue. Okay, good. And so now I need to figure out what the contributions on each part, right? So on the horizontal portions, on these horizontal strip, as little r goes to 0 and big R goes to infinity, as little r goes to 0 and the strip collapses, is going to be what? Well, we're going to integrate, big R goes to infinity. We're really integrating from what? Now on this top branch over here, you're going to integrate from 0 to infinity, right? Because that's where the x value is going to go from. And then what's the argument looking like? So now those are just, it's just going to be the log of plain old x over there, right? So it's going to be negative c, so it's going to be the exponential of negative c log x over x plus 1 dx. And then the bottom portion, the angle is pi, right? So I'm going to add that into the pi over here, right? So then I'm going to get another integral over here, integral from 0 to infinity of the exponential of negative c. And then log x, of course, that's still good. But now what? And of course, we're going to have a negative orientation of this thing too. So really, we're going to go from, let's be a little bit more pedantic about this. Let's actually go from infinity. Let's go from infinity, to be very clear, let's go from infinity up to 0, since I'm going backwards, right, on that orientation. Negative c log x plus what? Plus I times 2 pi, like that, over x plus 1 dx, okay? So all total, what's going to happen over here? So all total, these horizontal component, these horizontal parts equal what? Well, this is going to be a 1, and I can flip the infinity and the 0 and plot a negative e to the negative c pi, 2 pi I, right? So this is going to be a 1 minus e to the negative 2 pi I c, like that, times the integral from 0 to infinity of what? Of just x to the negative c over 1 plus x dx. So the horizontal contributions of this integral over here give me exactly these values, okay? Now I'd like to estimate the portions on the big circle and on the little circle, right? So let's do the big circle first, or the little circle first. So on the little circle, okay, what's z equal to there? Z is equal to r e to the I theta, like that. And so what is your integrand going to look like? Your integrand, so you're going to integrate, so what does the integral look like? You're going to have the integral. You're doing what? You're going from 2 pi to 0. Okay. Then you have to plug in what? Then you have to plug in the exponential of negative log c. Okay, so you're going to have exponential of negative c, and then log x, log of the modulus over here, which is going to be r, right? Because that's what you're in that little circle, plus I theta, right? Good. Over. What's z equal to there? Z is equal to r e to the I theta plus 1, and then r e to the I theta times an I d theta, right? And so if we estimate this over here, right, what's going to happen? I'm going to get a 2 pi for the length. Now r is small in this case, right? So r is small. E to the negative c I theta is unimodular, so when I do when I put the absolute values on the inside, this is going to go away, this is going to go away, and this is going to go away. So this is going to be less than or equal to the length of the interval, 2 pi, and then I'm going to have an exponential of the log of r to the negative c. So I'm going to have an r to the negative c, of course, right? Less than or equal to 2 pi from the length of the interval, and then an r to the negative c, an extra r over here, and then a what? And then the denominator, since r is small, I use a triangle inequality to do this, 1 minus r by the triangle inequality. Now, what can I say? C is between 0 and 1, so there's still a positive power of r in the denominator. So this tends to what? This tends to 0 as r goes to 0. So in other words, the contribution from the little circle tends to 0. Good? I can make the same exact estimate on the big circle, right? The big circle, the same exact estimate holds. So on the big circle is less than or equal to what? Is less than or equal to 2 pi, and then r capital negative c times r over r minus 1, like that. The triangle goes backwards. Now, of course, the power in the numerator is a 1 minus c, and there's a 1r in the denominator, so this goes to 0 as r approaches infinity. So as r approaches infinity, the big circle contribution goes to 0. As little r goes to 0, the little circle contribution goes to 0 as well. They both go to 0, right? Just for a different reason, right? Good. And so now what's our conclusion, therefore? Our conclusion, therefore, is that our integral, the integral from 0 to infinity of x to the negative c over 1 plus x dx is equal to this residue over here. So it's going to be a 2 pi I e to the negative I c pi. And I have to divide that by this coefficient factor over here, right? This 1 minus e to the negative 2 pi I c, like that, right? So I can put this exponential in the denominator, like so. And so this is equal to what? This is equal to 2 pi I over, I'll have an e to the I pi c minus e to the minus I pi c, right? And what does that look like over there? So I have a 2 and an I, and this is the difference. That looks like sine, but just upside down. So this is exactly equal to what? This is exactly equal to pi over the sine of what? Pi over the sine of pi times c over here. Beautiful, okay? Now, what's one thing we can know in particular, right? In particular, as c goes to 0, this diverges. Just note, as c goes to 0, this diverges. And as, yeah, and that's the whole point. So so what happens as c goes to 1? As c goes to 1, the sine of pi is also equal to 0. So as c goes to 1, the sine of pi is equal to, the sine of pi is also equal to 0, so it diverges also. This also diverges. Okay, and that's clear because the integral from 0 to infinity of when c is equal to 0, you get 1 over 1 plus x. That's clearly divergent, right? Except that's the logarithm at infinity diverges for that reason. Now, as c goes to 1, what's going to happen now? You have a logarithm at 0, right? So there's as c goes to 1, the logarithm's at 0. As c goes to 0, the logarithm's at 1. Why do I mention this fact that these things diverge as c goes to 1 and as to 0? Because these things are intimately related to the reciprocal of the gamma function and the roots of that function, or just the singularities of the gamma function, right? So these two things over here are going to pop up in the context when we study this function, analyzing the gamma function in further videos. Thank you very much.